Billions of years ago, when Einstein was creating his theories about space, he discovered something that seemed impossible to exist. What appeared to be just crazy math turned out to be one of the most mysterious things in the universe. White holes, the complete opposite of black holes. Imagine a place where nothing can enter, only exit. A place that spits matter and light into space like a giant cosmic fountain. While black holes suck everything in and never let anything escape, white holes do exactly the opposite. They expel everything and never let anything enter. But here's the scariest part. If you could spend just 5 seconds inside a white hole, you would experience something that defies all the laws of physics we know. Time would run backwards, gravity would push you out with infinite force, and you would see the birth of the universe happening in reverse. This forced scientists to ask a shocking question. Could the Big Bang actually have been the biggest white hole of all? Subscribe to the channel. Leave your like and comment from what part of the world you're watching, because now I'm going to tell you everything. Have you ever wondered what would happen if you somehow found yourself inside one of the most extreme and mysterious objects that theoretical physics has ever proposed? While black holes have captured our collective imagination for decades, their theoretical counterparts, white holes, remain even more enigmatic and possibly even more deadly. White holes stand as one of the most fascinating mathematical predictions to emerge from Einstein's general theory of relativity. Unlike their more famous cousins, black holes, which voraciously consume everything that crosses their event horizon, white holes do exactly the opposite. They expel matter and energy, making it theoretically impossible for anything to enter them. Imagine a cosmic fountain perpetually gushing out material into the universe with such force that nothing, not even light itself, could ever swim against this overwhelming current. The mathematics describing these theoretical entities emerges directly from the same Einstein field equations that predict the existence of black holes. When physicists solve these equations, they discover that certain solutions describe regions of spacetime that behave as cosmic drains, black holes, while other solutions describe cosmic sources, white holes. In the language of mathematics, white holes appear to be essentially black holes running backward in time. This time reversal aspect creates immediate problems for their existence in our universe. Our reality is governed by the second law of thermodynamics, which states that entropy, roughly speaking the measure of disorder in a system, always increases over time. White holes would represent a dramatic reversal of this fundamental principle, as they would organize and expel matter rather than increase disorder. This is why most theoretical physicists believe that while white holes are mathematically possible according to general relativity, they cannot naturally form or exist in our universe. But let's entertain the impossible for a moment. What if you somehow found yourself inside a white hole for just 5 seconds? The physics you would encounter would be so extreme that conventional understanding of space, time, and matter would completely break down. The scenario stretches our understanding of physics to its absolute limits and beyond. First, we need to recognize that the interior of a white hole represents a region where space-time curvature reaches extraordinary levels. The gravitational forces inside would be incomprehensibly intense. Near a white hole's singularity, the theoretical point of infinite density at its core, the laws of physics as we understand them simply cease to function. General relativity, which describes gravity as the curvature of spacetime, predicts its own failure under these conditions, as quantum effects must come into play. The defining characteristic of a white hole, its outward pushing force, would likely tear apart any matter at the subatomic level instantaneously. This isn't just about being pulled apart as with a black hole's tidal forces. Rather, Everything inside a white hole experiences an overwhelming repulsive force pushing outward toward the event horizon. Human tissue, organs, cells, molecules, atoms, and subatomic particles would all be instantly separated and accelerated outward at speeds approaching that of light. The energy density inside a white hole would be almost impossible to comprehend. Theoretical models suggest it would be so immense that conventional matter could not maintain its structure for even the briefest moment. At such energy levels, the fundamental forces of nature, electromagnetic, strong nuclear, and weak nuclear forces, would behave in ways completely alien to our everyday experience. The distinction between matter and energy would break down entirely, as described by Einstein's famous equation E equals mc squared. Your body would essentially become pure energy in conditions somewhat similar to those that existed during the first fractions of a second after the Big Bang. Even if by some miracle your physical form could remain intact for a fraction of a second, your sensory organs and nervous system would cease functioning before any meaningful experience could be registered. The human brain evolved to process information in an environment with stable, predictable physics. Inside a white hole, the physical basis for neural processing would be completely disrupted, making consciousness as we understand it physically impossible. From a quantum mechanical perspective, the situation becomes even more bizarre. Quantum field theory, which describes the behavior of subatomic particles, suggests that particles and antiparticles would be spontaneously created and annihilated at extraordinary rates within such extreme conditions. Your bodily matter would not only be torn apart, but would likely be transformed into exotic states of matter that have never been observed even in our most powerful particle accelerators. The temporal aspects of white holes add another layer of incomprehensibility to the scenario. Since white holes can be mathematically described as the time reverse of black holes, time itself might flow differently or even backward from the perspective of an external observer. This means that your 5 seconds inside might correspond to an entirely different duration from the perspective of the external universe. Some theoretical models even suggest that time as we understand it would cease to have meaning inside a white hole. Another fascinating aspect of white holes comes from certain interpretations of general relativity that connect them to black holes. Some theoretical physicists have proposed that white holes might represent the other side of black holes, possibly the exit points of wormholes. According to this speculation, matter that falls into a black hole might eventually emerge from a white hole, potentially in another region of space or time, or even in another universe altogether. However, even in these models, the journey through such a cosmic tunnel would subject matter to forces and conditions far beyond what any physical structure could withstand. The mathematics describing white holes also reveals another crucial point about their theoretical nature. They would be inherently unstable. Any matter or energy in the vicinity would be drawn toward the white hole's event horizon from the outside, creating a situation where the outward flow meets infalling material. This instability suggests that even if white holes could momentarily form, they would quickly collapse or transform into something else entirely. Research into white holes continues to evolve as physicists work to reconcile general relativity with quantum mechanics in the search for a unified theory of quantum gravity. Theories such as loop quantum gravity and string theory attempt to describe what happens in regions of extreme space-time curvature, potentially shedding new light on whether white holes could exist and what their properties might be. Some recent theoretical work has even suggested that tiny quantum white holes might have played a role in the early universe or could be produced in high-energy physics experiments, though detecting such phenomena remains beyond our current technological capabilities. Despite all this theoretical exploration, the conclusion remains inescapable. Spending 5 seconds inside a white hole would be physically impossible. No form of matter as we understand it could survive such extreme conditions, even for the briefest moment. The laws of physics, as we know them, break down so completely that the very question of human experience inside a white hole becomes meaningless. White holes remain fascinating mathematical constructs that push the boundaries of our understanding of physics. They remind us that the universe described by our equations can be far stranger than the universe we actually observe, and they continue to inspire theoretical physicists to explore the most extreme consequences of our most successful physical theories. While white holes remain fascinating mathematical constructs that challenge our understanding of physics, they introduce even more mind-bending implications when we consider their temporal properties. The bizarre nature of white holes extends far beyond just their extreme energy and outward-pushing forces. If we venture deeper into theoretical physics, we discover that these cosmic oddities create profound paradoxes in how time itself would function. Have you ever thought about what would happen if cause and effect stopped working the way we're used to? Inside a white hole, the normal rules of causality, the principle that causes precede their effects, would be fundamentally violated. This isn't just a minor quirk. It's a complete reversal of one of the most basic assumptions we make about how reality operates. The temporal properties of white holes generate these causality problems because they technically eject matter from the future toward the past. That's right. According to the mathematics of general relativity, white holes can be thought of as objects that run backward in time compared to the rest of the universe. This isn't just some wild speculation. It emerges directly from the same equations that successfully predict the behavior of gravity throughout the cosmos. If you somehow found yourself inside such an environment for even 5 seconds, you would be placed in a state where cause and effect might be completely uncoupled or even reversed. Imagine trying to navigate a reality where events happen before their causes, or where your actions might precede your intentions. Your brain, which evolved to process information in a specific temporal sequence, would be fundamentally incapable of making sense of such an environment. Some theoretical models take this even further, suggesting that inside a white hole, you might experience your own future and past simultaneously. This creates what physicists call an unresolvable paradox for conscious experience. Our minds construct our sense of self through memories of the past and anticipation of the future, all organized along a one-directional timeline. When that timeline becomes scrambled or multi-directional, the very foundation of consciousness gets undermined. The mathematics of general relativity reveals another fascinating aspect of white hole temporality: extreme time dilation. Even approaching a white hole's event horizon, the boundary marking the point of no exit, time would begin to behave very strangely. What might seem like 5 seconds to you could correspond to vastly different durations in the external universe, potentially millions or even billions of years. This isn't science fiction. It's a direct consequence of Einstein's equations that have been repeatedly verified in less extreme circumstances, such as with GPS satellites, where time dilation effects must be accounted for to maintain accuracy. Inside the white hole proper, the situation becomes even more radical. Time as a dimension might actually become space-like, while one spatial dimension becomes time-like. These technical terms describe a fundamental shift in how dimensions function. In practical terms, it means you could potentially move through what we normally consider time as easily as you currently move through space. You could potentially walk back and forth through moments the way you currently walk across a room. This dimensional shift would create a scenario where the conventional concept of now loses all meaning. In our normal experience, we perceive a single moment, the present, with the past fixed and the future yet to be determined. In a white hole's interior, this distinction would collapse. All moments might exist simultaneously from your perspective, creating what physicists sometimes call a block universe view, where past, present, and future are equally real and potentially accessible. The fundamental incompatibility between human neurological processing and the reversed temporal flow of a white hole creates another problem. Our brains process information through a series of electrochemical signals that rely on sequential causality. One neuron fires, causing another to fire, and so on. When that sequencing breaks down, consciousness as we understand it becomes physically impossible. During those theoretical 5 seconds inside a white hole, you likely wouldn't experience anything recognizable as thought or perception, since the physical basis for mental processes would be completely disrupted. Some theoretical physicists have proposed even more radical ideas about time inside white holes. For instance, time might become looped or circular rather than linear. In such a scenario, you might experience the same moments repeatedly, creating a situation similar to the philosophical concept of eternal return. Unlike fictional depictions of time loops where characters retain memories of previous cycles, in a white hole time loop, the laws of physics suggest your experience would reset completely with each iteration, making it impossible to perceive the repetition. The temporal weirdness extends to quantum mechanics as well. Quantum theory, which describes the behavior of matter and energy at the smallest scales, already contains some counterintuitive features regarding time. Certain quantum phenomena appear to involve particles that affect their own past states or that maintain correlations across time in ways that seem to violate classical causality. Inside a white hole, these quantum temporal effects would be amplified to macroscopic scales, potentially allowing quantum uncertainty to affect large-scale events in ways that make prediction and even retrospective understanding impossible. Another aspect of temporal paradoxes in white holes relates to information flow. Information in physics refers to the data required to fully describe a system's state. Under normal circumstances, information flows from the past to the future. In a white hole, this flow would be reversed, creating a situation where information about future states would determine past ones. This reversal creates profound problems for thermodynamics and entropy, which depend on the one-way flow of information through time. The entropy problem is particularly interesting. Entropy, a measure of disorder in a system, always increases over time according to the second law of thermodynamics. This law gives us the arrow of time that distinguishes past from future. In a white hole, entropy would decrease rather than increase, effectively reversing this arrow. You would witness processes running backward, broken objects reassembling themselves, scattered particles gathering together, and dispersed energy becoming concentrated. While mathematically possible, such phenomena have never been observed in our universe on macroscopic scales. Some theoretical models connect white holes to the concept of closed time-like curves, CTCS, paths through space-time that return to their starting point in both space and time. If CTCs exist within a white hole, they would allow for the possibility of information traveling backward in time, creating the potential for temporal paradoxes like the famous grandfather paradox, where one could theoretically travel back in time and prevent one's own existence. Physicists have proposed various resolution mechanisms for such paradoxes, including the Novikov self-consistency principle, which suggests that physics would somehow prevent contradictory outcomes. This peculiar temporal behavior also relates to questions about the origin of our universe. Some cosmological models propose that the Big Bang itself might have been a kind of white hole, a point from which all space, time, and matter emerged. If this were true, then the beginning of our universe would have embodied many of these same temporal paradoxes, with causality emerging only as the universe expanded and cooled. The intersection of quantum mechanics and general relativity in white hole physics creates even more temporal complications. These two pillars of modern physics treat time very differently. General relativity views time as a dimension woven into the fabric of space-time, while quantum mechanics treats it as a parameter against which changes are measured. Reconciling these views remains one of the greatest challenges in theoretical physics, and nowhere would this conflict be more apparent than inside a white hole. Some approaches to quantum gravity, the effort to unite these theories, suggest that at the smallest scales, time might not be continuous, but rather discrete, composed of indivisible units sometimes called chronons. In the extreme conditions of a white hole, these discrete units of time might become directly perceptible, creating an experience where time seems to stutter or jump rather than flow smoothly. Perhaps the most profound temporal implication of white holes comes from their relationship to black holes in certain unified theories. Some models suggest that black holes and white holes might be connected, with matter falling into a black hole eventually emerging from a white hole, possibly in another universe or another time. This connection creates a bridge, not just across space, but across time as well, potentially linking different eras or even different phases of the universe's existence. While all of these ideas remain firmly in the realm of theoretical physics, they highlight how white holes challenge our most fundamental assumptions about reality. They force us to confront the possibility that time, which seems so basic to our experience, might be far more complex and malleable than we typically imagine. The temporal paradoxes and causality violations associated with white holes aren't just academic curiosities. They reveal the limits of our understanding and point toward deeper structures underlying the physics of our universe. Beyond the temporal paradoxes that white holes present, their physical environment would be even more immediately threatening to human existence. The exotic physics of these theoretical cosmic objects goes far beyond just warping time. They would create what might be the most hostile radiation environment conceivable in our universe. If the temporal effects weren't enough to render human experience impossible, the sheer radiation intensity would ensure that no biological structure could remain intact even for microseconds. White holes are theoretically predicted to be extraordinary emitters of radiation across the entire electromagnetic spectrum. From radio waves to visible light to gamma rays, these cosmic fountains would spew energy outward at intensities that would make even the most extreme known cosmic events, supernovas, gamma-ray bursts, or black hole accretion disks, seem tame by comparison. The radiation wouldn't just be intense, it would be comprehensive, bombarding any matter with every frequency of electromagnetic energy simultaneously. What would this mean for human biology? The short answer is complete and immediate cellular destruction. Human tissue exposed to this radiation bath would experience simultaneous damage across all cellular structures. To understand why, we need to look at how radiation affects living tissue. Under normal circumstances, radiation damage occurs when high-energy particles or waves transfer their energy to the atoms and molecules in our cells. This energy transfer can break chemical bonds, create free radicals, and damage crucial cellular components like DNA. On Earth, radiation exposure is measured in units called sieverts, with anything above 5 sieverts generally considered a lethal dose for humans. Near a white hole, theoretical calculations suggest radiation levels would be millions or even billions of times beyond this lethal threshold. At such extreme levels, radiation wouldn't just damage DNA, it would shatter molecular structures throughout every cell in your body simultaneously. The complete breakdown of DNA and cellular machinery would occur within microseconds, so quickly that pain signals wouldn't even have time to reach your brain before consciousness ceased. Your nervous system, which operates through electrochemical signals traveling at finite speeds, would be overwhelmed before it could even begin to process what was happening. In essence, you wouldn't feel pain because the very structures needed to experience pain would be destroyed too quickly. The radiation environment inside a white hole wouldn't just be quantitatively extreme, it might be qualitatively different from anything we've observed. Theoretical calculations suggest temperatures inside a white hole could reach trillions of degrees. At such temperatures, matter doesn't exist in any form we'd recognize. Instead, it forms a state called quark-gluon plasma, where the fundamental building blocks of protons and neutrons float freely rather than binding together into atomic nuclei. What does this mean in practical terms? Your body would be instantly converted into plasma, not blood plasma, but a state of matter similar to what existed in the first microseconds after the Big Bang. This wouldn't be a gradual process. The conversion would happen essentially instantaneously due to the extreme energy transfer. Your entire physical structure would be reduced to its most fundamental components faster than any biological process could respond. Some speculative physics models go even further, suggesting that exotic radiation types unknown in our universe might also be present in white holes. These theoretical forms of radiation might interact with matter in ways fundamentally different from conventional physics. For instance, some theories in quantum gravity suggest the possibility of gravitational radiation with properties unlike anything we've detected with our current instruments. The combined effect of known and exotic radiation would make a white hole perhaps the most lethal environment conceivable in physics. This renders the question of a 5-second survival entirely moot. Survival wouldn't be measured in seconds or even milliseconds, but rather in timescales relevant to subatomic processes. Another interesting aspect of white hole radiation relates to its origin. Unlike most radiation sources we're familiar with, which emit energy through specific physical processes like nuclear decay or thermal emission, white hole radiation would be a fundamental property of spacetime itself. The extreme curvature of spacetime near and within a white hole would generate radiation through quantum effects similar to what Stephen Hawking described for black holes, only in reverse. Hawking radiation, named after the famous physicist, describes how black holes actually emit a small amount of radiation due to quantum effects near their event horizons. For white holes, this process would be dramatically amplified. Instead of the subtle quantum emission predicted for black holes, white holes would produce an overwhelming torrent of radiation as a direct consequence of their spacetime geometry. The radiation environment would also be notably different from region to region within a white hole's structure. Near the event horizon, the boundary that nothing can enter but everything must exit, the radiation would already be lethal. But as you move toward the theoretical central singularity, the radiation intensity would increase exponentially. This creates a situation where not only would survival be impossible, but different parts of your body would be exposed to drastically different radiation levels simultaneously, further accelerating tissue breakdown. Interestingly, the radiation from a white hole would also carry information, at least in theory. Just as Hawking radiation from black holes is thought to eventually contain information about everything that fell into the black hole, radiation from a white hole might contain information about whatever exists on the other side, assuming white holes connect to other regions of spacetime. This information would be encoded in the precise quantum state of the radiation. though decoding it would require technology far beyond our current capabilities. Beyond electromagnetic radiation, white holes would theoretically produce intense gravitational radiation, ripples in space-time itself. These gravitational waves would be far more powerful than those we've detected from black hole mergers using instruments like LIGO, Laser Interferometer Gravitational Wave Observatory. The human body isn't directly sensitive to gravitational waves, but at the intensities predicted near white holes, these space-time ripples would be strong enough to physically tear matter apart through tidal forces. The radiation environment would also feature an extreme flux of high-energy particles. Cosmic rays, which are actually particles rather than rays, can be dangerous even under normal cosmic conditions. Astronauts in space receive careful monitoring of their cosmic ray exposure. Near a white hole, the particle flux would be incomprehensibly greater than anything encountered in space exploration. These particles, accelerated to nearly the speed of light, would pass through human tissue, depositing enormous energy along their paths. When high-energy particles pass through matter, they create what physicists call ionization tracks, paths of damaged molecules where electrons have been stripped away from atoms. In a normal radiation exposure scenario, these tracks occur occasionally throughout tissue. In a white hole environment, the particle flux would be so intense that ionization would happen simultaneously throughout every cell, effectively converting all bodily fluids to an ionized state instantaneously. The biological effects wouldn't stop at direct radiation damage. Secondary effects would be equally devastating. When high-energy radiation interacts with matter, it produces secondary particles and radiation in a process called a particle shower. Your body would not only be exposed to the primary radiation from the white hole, but would itself become a source of secondary radiation as particles interacted with your atoms. This creates a cascade effect that amplifies the already overwhelming damage. Another biological consideration is the effect on water molecules, which make up approximately 70% of the human body. When exposed to intense radiation, water undergoes radiolysis, breaking down into reactive fragments including hydrogen and hydroxyl radicals. These radicals are highly reactive chemical species that immediately attack nearby biological molecules. Under white hole conditions, all bodily water would undergo radiolysis essentially simultaneously, creating an internal chemical environment incompatible with molecular integrity. Some theoretical models of white holes incorporate aspects of quantum gravity, attempts to reconcile general relativity with quantum mechanics. These models suggest that at the energy scales present in white holes, the nature of radiation itself might change. Particles and waves might behave according to physics beyond our standard model, potentially interacting with matter in unpredictable ways. Some speculative theories suggest exotic processes like micro-black hole formation or string excitations could occur within irradiated matter. The radiation from a white hole wouldn't just affect individual cells or organisms, it would sterilize vast regions of space around it. Any matter ejected from a white hole would remain highly radioactive, potentially creating zones of intense radiation extending far beyond the white hole itself. This has led some theoretical physicists to speculate that if white holes existed in the early universe, they might have influenced the development of structure and chemistry in surrounding space. The combination of all these radiation effects makes a white hole perhaps the most hostile environment that physics can describe. No known form of matter could maintain its structure under such conditions, and no biological process could function. The extreme radiation environment represents a fundamental limit to both technology and biology, a region where the physical laws that allow for complex structures and processes break down completely. While human survival in such an environment is clearly impossible, understanding these extreme conditions helps physicists push the boundaries of our theories and explore the limits of physical law. The study of white hole radiation environments connects to broader questions in physics about the nature of space-time, the behavior of matter under extreme conditions, and the fundamental limits of physical existence in our universe. Beyond the intense radiation that would destroy any physical body in a white hole, there lies an even deeper level of reality affected by these theoretical cosmic objects. The quantum information that describes a person at the most fundamental level. While the radiation effects represent the immediate physical danger, the fate of information in a white hole presents some of the most perplexing paradoxes in theoretical physics. These information paradoxes reveal problems that go far beyond mere survival and touch on the fundamental nature of reality itself. In quantum physics, information has a special meaning. It's not just about facts or data as we typically think of them, but rather the complete description of a quantum system, the precise quantum state of every particle making up your body and how they're all related to each other. This quantum information is governed by strict rules in normal physics. One of the most important is called unitarity, which essentially means that information cannot be destroyed. It can only change form. This preservation of information has led to famous paradoxes in black hole physics. When matter falls into a black hole, it seems the information is lost forever behind the event horizon, potentially violating unitarity. Physicists have debated this black hole information paradox for decades, but for white holes, the paradox runs in reverse, creating even stranger implications. For white holes, instead of information seemingly disappearing, it appears to emerge from nowhere. If a white hole is constantly expelling matter and energy, where does the information describing this material come from? This reverse information paradox creates a fundamental problem for physics, which generally assumes that information has a causal history. In a white hole, information appears without a past, challenging basic assumptions about how reality works. Spending 5 seconds inside a white hole would mean your quantum information, the complete quantum state describing your atoms and their relationships, would be subject to conditions that violate these quantum principles. Your body's quantum information would face a situation where normal rules of information conservation and causality break down completely. What does this mean in practical terms? Theoretical physics suggests that the quantum wave function describing you might undergo what physicists call decoherence in novel and extreme ways. Decoherence is the process by which quantum systems lose their delicate quantum properties through interaction with their environment. Under normal conditions, this happens extremely quickly for large objects like humans, which is why we don't observe quantum effects like superposition in everyday life. In a white hole environment, decoherence would happen through mechanisms completely different from those in our familiar world. The extreme space-time curvature and energy densities would create decoherence channels that don't exist under normal conditions. This might potentially split the observer into quantum superpositions that span multiple realities or universe states. What would this feel like? The honest answer is that human experience as we understand it would be impossible. Our consciousness emerges from physical processes that depend on relatively stable quantum states in our neural structures. When those quantum states undergo extreme and unusual decoherence, the physical basis for consciousness itself breaks down. It's not just that you wouldn't survive, it's that you, as a coherent entity, might cease to exist in any meaningful sense, with your quantum information scattered across multiple possible states of reality. Some cutting-edge theories in quantum gravity, attempts to reconcile quantum mechanics with general relativity, suggest even more radical possibilities. These theories propose that inside a white hole, the distinction between observer and environment might break down entirely. This isn't just a poetic way of saying you'd be destroyed. It represents a fundamental blurring of the boundary that separates you from not you at the quantum level. In normal physics, we can clearly distinguish between a system like a human body and its environment. This distinction is what allows us to talk about measurements, observations, and experiences. But in the extreme conditions of a white hole, this separation might become physically meaningless. Without this distinction, the very concept of an observer becomes problematic, leading to a state where self-awareness becomes physically impossible. The mathematical formalism that physicists use to describe these situations, quantum field theory in curved spacetime, points to another bizarre aspect of white hole physics. In this framework, particles aren't fundamental objects, but rather excitations in quantum fields that permeate all of space. When spacetime becomes extremely curved, as it would be in a white hole, these quantum fields behave in extraordinary ways. One consequence is that particle creation and annihilation would occur at rates far beyond anything we observe in normal physics. Virtual particles, which normally pop in and out of existence too quickly to directly observe, would become abundant and long-lived enough to interact with real particles. The vacuum itself would be seething with particle activity, creating a situation where the very concept of distinct particles making up your body would become meaningless. Instead of being composed of stable protons, neutrons, and electrons, your body's matter would dissolve into a constantly shifting sea of quantum field excitations without clear boundaries or identities. The atoms that make up your cells wouldn't maintain their integrity for even the briefest moment, as the fields from which they emerge would be fluctuating too rapidly and intensely. Certain approaches to quantum gravity, like loop quantum gravity or causal set theory, take this even further. These theories suggest that in conditions of extreme energy and spacetime curvature, spacetime itself becomes quantized, broken into discrete units rather than forming a continuous fabric. If these theories are correct, then in a white hole, you wouldn't just experience unusual physics within spacetime. You'd experience the breakdown of spacetime itself into its quantum constituents. What would this mean for an observer? It suggests that in such extreme conditions, existence itself wouldn't be continuous, but rather would unfold in discrete frames of reality. Consciousness, which seems to require continuity to function, would be impossible in such a discretized reality. Your 5 seconds inside a white hole wouldn't be experienced as a smooth passage of time, but might instead manifest as disconnected moments without the continuity needed for coherent experience. Another quantum effect relevant to white holes comes from a theoretical phenomenon called the Unruh effect. This effect predicts that an accelerating observer will perceive the vacuum around them as filled with thermal radiation. In a white hole, where matter is being constantly accelerated outward at enormous rates, the Unruh effect would be amplified to extreme levels. From the perspective of quantum information, this means your body wouldn't just be physically heated. The quantum fields making up your atoms would perceive themselves as immersed in an intense thermal bath, further disrupting any chance of maintaining coherent quantum states. Some theoretical physicists have also explored how quantum entanglement would behave in white hole scenarios. Entanglement is a quantum phenomenon where particles become correlated in ways that can't be explained by classical physics. In normal conditions, maintaining entanglement is extremely difficult because interactions with the environment quickly destroy these delicate quantum correlations. In a white hole, the intense environment would create patterns of entanglement unlike anything we observe in laboratory physics. Your body's particles, which normally maintain certain entanglement patterns that are part of biological structures, would find these correlations completely disrupted. New entanglements would form and dissolve at extraordinary rates, creating quantum information patterns that bear no resemblance to those of a living organism. Your quantum information wouldn't just be destroyed, it would be transformed into states that have no counterpart in our familiar reality. The information paradoxes extend to questions about reversibility as well. According to the laws of quantum mechanics, fundamental processes should be reversible in time. Run the equations backward, and you get physically possible results. But white holes seem to violate this principle by their very nature. They expel matter and energy without any clear history, creating an arrow of time that seems to emerge from nowhere. For an observer inside a white hole, this irreversibility would manifest in the complete inability to reconstruct their past states. The quantum information describing your previous moments would be unavailable in principle, not just in practice. This represents a breakdown of quantum mechanics at a fundamental level, suggesting that inside a white hole, the rules of physics, as we understand them, simply cease to apply. Some speculative theories attempt to resolve these paradoxes by proposing that white holes connect to other regions of space-time or even other universes. In these models, the quantum information isn't created from nothing but rather transferred from elsewhere through space-time connections not visible from our universe. If such theories are correct, then your 5 seconds inside a white hole might involve your quantum information becoming entangled with information from entirely different regions of the multiverse. The implications for identity and consciousness in such scenarios become profoundly strange. If your quantum information becomes entangled with information from other universes, does this represent a kind of merging of identity across realities? Again, such questions likely have no meaningful answer because the physical basis for consciousness would be disrupted before any such experience could register. Perhaps the most radical perspective comes from some approaches to quantum gravity that suggest information itself is the fundamental reality, with space, time, and matter emerging from networks of quantum information. In these frameworks, a white hole represents a kind of information processing structure of extraordinary complexity, a node in the quantum information network where information flows in patterns completely unlike those in ordinary spacetime. From this perspective, spending 5 seconds inside a white hole wouldn't just mean experiencing unusual physics. It would mean having your own quantum information processed through mechanisms that transcend our normal concepts of physical reality. The result wouldn't be death in any conventional sense, but rather a transformation of information so complete that no continuity with your previous state would remain. These information paradoxes remind us that at the deepest levels of reality, our intuitive notions of existence, identity, and experience may not apply. White holes challenge not just our understanding of how matter behaves under extreme conditions, but our very concepts of what reality is made of at its most fundamental level. They represent regions where our best physical theories make predictions so strange that we struggle to translate them into any framework meaningful to human experience. The fundamental reality of quantum information leads us directly to another extraordinary aspect of white holes, how they would distort and transform the very fabric of space itself. While we've explored how matter, energy, and information would behave in a white hole, we haven't yet fully grasped how the underlying spatial structure would be altered. This spatial distortion represents perhaps the most alien aspect of white hole physics, creating conditions that would make conventional human perception physically impossible. The extreme curvature of space-time within a white hole would distort spatial relationships to such a degree that conventional three-dimensional space would become completely unrecognizable. In normal space, we experience three spatial dimensions that behave in predictable ways: forward-backward, left-right, and up-down. These dimensions allow us to navigate our environment and understand spatial relationships between objects. But inside a white hole, this familiar structure breaks down completely. General relativity tells us that mass and energy curve space-time. The more massive an object, the more it warps the fabric of reality around it. We can observe mild versions of this curvature in our universe, like how light bends around massive objects like the sun. But in a white hole, the curvature becomes so extreme that space essentially folds in on itself in ways that defy visualization. Some theoretical models suggest that near the core of a white hole, additional spatial dimensions might become accessible or perceptible. These extra dimensions normally remain compactified or hidden from our experience. String theory, for instance, proposes that our universe actually contains 10 or 11 dimensions, with most of them curled up so tightly that we never notice them in everyday life. But in the extreme conditions of a white hole, these dimensions might temporarily unfurl, exposing a human observer to a higher dimensional reality. What would it mean to perceive additional spatial dimensions? Our brains evolved specifically to process information in three spatial dimensions. We have no neural framework for comprehending what a fourth or fifth spatial dimension would look like. This isn't just a limitation of imagination. It's a fundamental constraint built into our sensory and cognitive systems. If these additional dimensions became perceptible inside a white hole, the resulting sensory input would be completely unprocessable by the human brain. It would be like trying to make a one-dimensional line understand what a cube is. The mathematics of white hole interiors indicates something even stranger. Spatial distances might become negative or imaginary values. In conventional mathematics, we use negative numbers and imaginary numbers based on the square root of -1 all the time. They're perfectly valid mathematical concepts. But in our physical experience, spatial distances are always positive real numbers. You can't walk -5 meters or move imaginary 3 meters in any direction. In a white hole, however, the equations of general relativity yield solutions where spatial coordinates can take on these exotic values. What would this mean in practical terms? Negative distances might represent a kind of anti-space where the normal relationships between points are inverted. Imaginary distances would represent something even more alien. Spatial relationships that simply have no counterpart in our everyday experience. If you somehow survived 5 seconds in such an environment, you might experience a condition where here and there lose all conventional meaning. Points that appear distant might be connected through space-time shortcuts created by extreme curvature. You might find that moving in what seems like one direction actually takes you in another, or that all directions simultaneously lead both toward and away from where you want to go. This breakdown of normal spatial relationships would also affect how objects relate to each other. In our familiar space, two objects cannot occupy the same location, and to get from one point to another, you must traverse all intermediate points. But in the warped space of a white hole, these basic principles might not apply. Objects might partially overlap in ways impossible in normal space, or movement might become discontinuous, allowing jumps from one location to another without passing through the intervening space. Certain theories in loop quantum gravity, one approach to unifying quantum mechanics and general relativity, suggest something even more radical. According to these models, space inside a white hole becomes granular rather than continuous, breaking down into fundamental atoms of space at the Planck scale, approximately 10 to the negative 35th meters. In our normal experience, space seems perfectly smooth and continuous. You can always divide any distance into smaller and smaller portions, but at the quantum level there may be a fundamental minimum length below which space cannot be further divided. In a white hole, these discrete units of space would become relevant to macroscopic experience. Movement would no longer be smooth but would occur in tiny jumps from one spatial atom to the next. This would make conventional motion as we understand it physically impossible. Your body, which relies on continuous spatial relationships between its parts, would find its fundamental structure incompatible with this granular spatial environment. The directional nature of space would likely be altered as well, potentially creating a situation where all directions lead outward toward the event horizon. In normal space, if you pick a direction and keep moving that way, you'll continue along a straight line. But in the severely curved space of a white hole, all paths might curve toward the exit, regardless of which way you think you're heading. This creates a spatial topology where the concept of choosing a direction becomes meaningless. All roads literally lead to Rome, or in this case, to the white hole's event horizon. This spatial distortion would also affect how different parts of your body relate to each other. Your cells and organs maintain specific spatial relationships that are necessary for biological function. When space itself no longer maintains consistent properties, these relationships break down. Different parts of your body might experience different spatial geometries simultaneously, making coordinated biological processes impossible. Your heart couldn't pump blood effectively if the spatial path between it and your other organs kept changing in unpredictable ways. Some theoretical models of white holes incorporate ideas from holographic principles, which suggest that all the information in a three-dimensional volume can be encoded on its two-dimensional surface. If these principles apply to white holes, then the three-dimensional space we experience might actually be a projection from information encoded on the white hole's event horizon. Inside such a structure, you might experience space as simultaneously three-dimensional and two-dimensional, creating perceptual contradictions that no biological brain could process. Another fascinating aspect of spatial distortion in white holes involves what physicists call closed time-like curves. These are paths through space-time that loop back on themselves, allowing theoretical travel into one's own past. While normally discussed in terms of their temporal implications, they also create profound spatial paradoxes. In a region with closed time-like curves, you might move forward continuously, only to find yourself returning to your starting point not just in location but in time as well. The spatial and temporal aspects become so intertwined that they can't be meaningfully separated. The concept of distance itself becomes problematic in a white hole. In normal space, we can clearly define the distance between 2 points using the familiar Euclidean or Minkowskian metrics. But in the extreme curvature of a white hole, conventional distance measures break down. 2 points that appear close together when measured one way might be infinitely far apart when measured differently. This creates a situation where the answer to "how far is it from point A to point B" becomes fundamentally ambiguous. Some theoretical physicists have proposed that in regions of extreme space-time curvature, space might develop what are called non-commutative properties. In normal space, the order of operations doesn't matter. Moving 3 meters north and then 2 meters east gets you to the same place as moving 2 meters north and then 3 meters east and then 3 meters north. But in non-commutative space, The order would matter. Moving in one direction and then another would take you to a different location than if you performed those same movements in the opposite order. If white holes feature non-commutative space, navigation would become fundamentally impossible as we understand it. You couldn't plan a path from one point to another because the very concept of a path would depend on the specific sequence of infinitesimal movements that compose it. Each tiny adjustment in direction would alter not just where you're going, but the entire spatial framework you're operating within. This spatial complexity extends to the concept of boundaries as well. In normal space, we can clearly define the inside and outside of objects or regions. But in a white hole, these distinctions might blur. The boundary between inside and outside might itself have spatial extent, creating transition regions where you would be neither fully within nor fully outside a given volume. Your body, which relies on clear boundaries between its interior and the external environment, would face fundamental challenges to maintaining its physical integrity. The most mind-bending aspect of spatial distortion in white holes comes from some quantum gravity theories that suggest space itself might be emergent rather than fundamental. In these frameworks, what we experience as space is actually a manifestation of more basic quantum entanglement relationships between fundamental entities. Inside a white hole, these entanglement patterns would be so radically altered that space, as we understand it, might temporarily cease to exist altogether, replaced by pure quantum relationships without spatial character. For a human observer, this would mean finding yourself in a condition where the concept of location becomes not just distorted, but meaningless. The question, "Where am I?" would have no answer because where presupposes a spatial framework that no longer exists. This represents perhaps the most profound spatial paradox of white holes, the possibility that they create conditions where space itself is temporarily abolished. These spatial distortions reveal that white holes wouldn't just be hostile to human life due to extreme energy or radiation. They would create conditions where the basic spatial framework required for any kind of embodied existence breaks down completely. Even if we could somehow shield against the energy and radiation, the spatial distortions alone would make survival impossible. Our physical bodies and minds are adapted to function within the specific spatial geometry of our universe. When that geometry changes radically, no adaptation could possibly maintain biological function. The fundamental breakdown of spatial geometry in a white hole brings us to perhaps the most fascinating question of all. What would happen to consciousness itself in such an environment? While we've established that biological survival would be physically impossible, this leaves open the theoretical question of what might happen to perception and awareness if we could somehow observe white hole conditions. Human consciousness, after all, isn't just a biological process. It's an intricate symphony of neural activity that gives rise to our subjective experience of reality. Our consciousness relies on specific electrochemical processes occurring within a narrow range of physical conditions. The human brain contains approximately 86 billion neurons, forming trillions of connections, all operating through precisely timed electrical impulses and chemical transmissions. These processes have evolved to function within Earth's relatively stable environment. Inside a white hole, this delicate neural machinery would encounter conditions that would prevent normal functioning at every level. The extreme conditions would likely cause perception to break down completely. Our sensory systems, vision, hearing, touch, taste, and smell, have evolved to detect and process specific types of information from our environment. Vision relies on photons interacting with specialized cells in our retinas. In a white hole, the overwhelming flood of photons across all wavelengths would immediately overload these cells. Similar overloads would occur with all other sensory systems simultaneously. Even if our sensory organs could somehow withstand this onslaught, the information they gathered would be so alien and chaotic that our brains couldn't possibly interpret it in any meaningful way. Our neural circuitry is specifically wired to identify patterns relevant to survival in our normal environment. When faced with sensory input that bears no resemblance to anything in our evolutionary history, these pattern recognition systems would fail completely. This sensory overload would create experiences that cannot be encoded in memory or later described using language based on our universe's physics. Human memory formation relies on specific neural pathways strengthening through repeated activation. In a white hole environment, the physical basis for these pathways would be disrupted before memories could form. Any theoretical observer who somehow survived would likely have no recollection of the experience, not because they would forget, but because their brain would never have been able to encode the experience in the first place. Some theoretical physicists have speculated about what consciousness might experience in such extreme conditions. One possibility is that the normal boundaries of perception might dissolve entirely. In our everyday experience, we perceive distinct sensory modalities. Sight is different from sound, which is different from touch. This separation occurs because different neural pathways process different types of sensory information. Under white hole conditions, with all neural systems simultaneously overwhelmed, these distinctions might collapse. The result might be something like synesthesia taken to an extreme degree. Synesthesia is a condition where stimulation of one sensory pathway leads to automatic, involuntary experiences in a second sensory pathway, like seeing sounds or tasting colors. In a white hole, all sensory boundaries might completely dissolve, creating a state where sensory information becomes an undifferentiated flood without the usual categorical distinctions. The brain's processing mechanisms rely on a specific arrow of time and causality, both of which would be severely disrupted in a white hole. Our neural processes depend on causes preceding effects. A neuron fires, triggering downstream neurons to fire in sequence. When causality breaks down, this sequential processing becomes impossible. Instead of the normal flow of neural activation, you might experience a state where past, present, and future perceptions occur simultaneously. This simultaneous perception of multiple time frames would be completely unprocessable by normal consciousness. Our sense of self is intimately tied to experiencing a coherent sequence of moments. When that sequence breaks down, the continuity that underlies self-awareness would fragment. Rather than experiencing a unified self moving through time, consciousness might dissolve into disconnected fragments of awareness without any integrating center. Some theories suggest that consciousness under such exotic conditions might experience a state similar to what some call non-dual awareness, where the distinction between observer and observed completely collapses. In normal perception, we experience a clear boundary between self and world, between the perceiver and what is perceived. This boundary is maintained by specific brain processes that distinguish between internal and external stimuli. In a white hole, with normal brain function impossible, this fundamental perceptual boundary might dissolve. The result wouldn't be an expanded or enlightened form of consciousness, despite superficial similarities to descriptions from certain contemplative traditions. Instead, it would represent a breakdown of the physical structures that make consciousness possible in the first place. Any apparent similarity to transcendent states would be misleading, like comparing a computer that's been smashed with a hammer to one running advanced software. Both may not be functioning normally, but for very different reasons. The temporal disruptions inside a white hole would create additional perceptual paradoxes. Our perception of time relies on the hippocampus and other brain regions that sequence events and create our sense of past, present, and future. In a white hole, with time itself behaving abnormally, these sequencing mechanisms would fail. You might experience what neurologists call achronia, a condition where the normal sense of temporal order breaks down completely. In cases of brain injury that affect temporal processing, patients sometimes report experiences like seeing the end of an event before its beginning, or being unable to determine which of two events happened first. In a white hole, these temporal distortions would be amplified to an extreme degree. Rather than the normal flow of moments that characterizes conscious experience, you might perceive events in reverse order, simultaneously, or in constantly shifting arrangements that follow no consistent pattern. The disruption wouldn't be limited to sensory perception. Our emotional responses, which rely on structures like the amygdala and systems of neurotransmitters such as serotonin and dopamine, would also face fundamental disruption. Emotions evolved as adaptive responses to environmental conditions. Fear helps us avoid danger, while pleasure rewards beneficial behaviors. In a white hole environment, where normal environmental conditions no longer apply, emotional responses would become untethered from their usual causes and functions. This emotional disruption might create states where emotional responses occur without corresponding stimuli, or where multiple contradictory emotions activate simultaneously. Instead of feeling fear or surprise at the extraordinary conditions, normal responses to unusual situations, you might experience emotional states that have no counterpart in ordinary human experience. As the physical basis for normal emotional processing breaks down, cognitive functions like reasoning, decision-making, and problem-solving would be equally affected. These processes rely on the prefrontal cortex and its connections to other brain regions, all operating according to the normal laws of physics. In a white hole with those laws breaking down, cognitive operations would become impossible. Logical thinking depends on stable cause and effect relationships that wouldn't exist in such an environment. Some theoretical physicists have suggested more exotic possibilities for consciousness in extreme space-time conditions. Roger Penrose, a prominent mathematician and physicist, has proposed that consciousness might involve quantum processes occurring in neural structures called microtubules. If this controversial theory has any merit, then in the extreme quantum conditions of a white hole, consciousness might briefly experience what Penrose calls objective reduction, a collapse of quantum possibilities that might momentarily reveal aspects of quantum consciousness normally hidden in ordinary conditions. This wouldn't represent enhanced awareness, but rather a glimpse of the quantum underpinnings of consciousness, just as those underpinnings themselves break down. It would be like seeing the code behind a computer program at the exact moment the computer is being destroyed. A momentary insight immediately followed by complete system failure. The relationship between consciousness and quantum mechanics remains highly speculative, but some theories suggest connections between quantum entanglement and the binding problem in consciousness, how our brains integrate diverse sensory inputs into unified perceptual experiences. In a white hole, with quantum processes operating far outside their normal parameters, any quantum aspects of consciousness would be pushed to extremes beyond anything evolution has prepared our brains to handle. This raises profound questions about whether consciousness could exist at all in such an environment, even theoretically. Consciousness as we understand it emerges from specific physical processes occurring in the brain. When those processes become physically impossible, consciousness itself may simply not be able to arise or persist. Rather than experiencing white hole conditions, you might simply cease to be conscious at all until returning to an environment where the physical basis for consciousness can be restored. Some theoretical physicists have proposed that consciousness might exist in forms radically different from those we're familiar with. Information processing, which underlies consciousness in some way, might theoretically occur through substrates other than biological brains. But even these alternative forms would require some stable physical laws to operate. In a white hole, with physics itself breaking down, even exotic forms of consciousness would likely fail. This exploration of consciousness under white hole conditions reminds us of how fundamentally our subjective experience depends on the stable physics of our universe. The seemingly simple act of having a conscious experience requires precisely the kind of orderly, consistent natural laws that white holes would violate. While we can mathematically describe these exotic cosmic objects, the subjective experience they would create, or more likely prevent, remains beyond our ability to truly comprehend. The way our consciousness is bound to the physical laws of our universe points to an even more fundamental aspect of what would happen inside a white hole: the complete transformation of our physical matter. While consciousness would cease to function in any recognizable way, the actual material components that make up our bodies would undergo even more dramatic changes. In the extreme environment of a white hole, the very distinction between matter and energy would break down, triggering transformations far beyond anything seen in normal physics. Our bodies are made of ordinary matter, mostly carbon, hydrogen, oxygen, nitrogen, calcium, and phosphorus, arranged into complex molecules that form cells and tissues. This matter normally exists in stable states, with atoms maintaining their structure through the delicate balance of fundamental forces. But in a white hole, this stability would instantly vanish as the tremendous energies present would trigger processes that would completely transform our physical form. One of the most immediate effects would be nuclear reactions occurring throughout every atom in your body. Under normal conditions, nuclear fusion, where atomic nuclei combine to form heavier elements, only occurs in extreme environments like the cores of stars, where temperatures reach millions of degrees. Inside a white hole, the energy densities would far exceed even stellar cores, potentially triggering fusion reactions throughout every atom in your body simultaneously. Similarly, nuclear fission, the splitting of heavy atomic nuclei into lighter elements, would occur alongside fusion. The atoms that make up your tissues would essentially undergo simultaneous fusion and fission in a chaotic cascade of nuclear reactions. This wouldn't happen gradually, but would affect all atoms nearly instantaneously due to the extreme energy transfer throughout your body's matter. The tremendous energies involved would almost certainly convert your physical form into various states of exotic matter that rarely exist in our universe under normal conditions. One possibility is that your body would temporarily exist as what physicists call a quark-gluon plasma. This state of matter existed only in the earliest moments after the Big Bang, when the universe was still so hot and dense that protons and neutrons couldn't form. Instead, their constituent particles, quarks and gluons, floated freely in a kind of soup. In this state, the atoms and molecules that make up your body would no longer exist as distinct entities. The boundaries between different atoms would dissolve as the fundamental particles from which they're made become deconfined, freed from the strong nuclear force that normally binds them into protons and neutrons. Your entire body would essentially become a cloud of elementary particles without the organizational structure that normally defines biological matter. The outward-pushing nature of a white hole would create another dramatic effect. Unlike black holes, which compress matter to extreme densities, white holes expel matter outward. Your body's material would experience this repulsive force, causing rapid expansion. Your physical form would effectively be converted into an expanding cloud of particles and radiation spreading outward at speeds approaching that of light. This expansion wouldn't just separate different parts of your body from each other. It would also affect the subatomic structure of every atom. The space between elementary particles would increase rapidly, causing your matter to become less dense as it's pushed outward by the white hole's repulsive effects. From the perspective of an outside observer, if any could somehow witness this, your body would appear to transform into an expanding shell of energy and particles. The behavior of fundamental forces, the strong nuclear force, weak nuclear force, electromagnetic force, and gravity, would be radically altered in a white hole environment. Under normal conditions, these forces maintain specific relationships that allow atoms and molecules to exist in stable configurations. In the extreme environment of a white hole, these relationships would change dramatically. The strong nuclear force, which normally binds protons and neutrons together in atomic nuclei, would behave differently under such extreme energy conditions. At very high energies, this force actually becomes weaker, a phenomenon called asymptotic freedom. In a white hole, this weakening would contribute to the breakdown of atomic nuclei throughout your body. Similarly, the electromagnetic force, which governs chemical bonds and keeps electrons orbiting atomic nuclei, would be overwhelmed by the extreme energies present. The chemical bonds that hold your body's molecules together would break instantly, and the electrons would be stripped from their orbitals, creating a state of highly ionized matter. Even more exotic transformations might occur due to the extreme conditions. Some speculative physics suggests that in such environments, your matter might briefly exist in multiple quantum states simultaneously. Quantum mechanics tells us that particles can exist in superpositions, multiple states at once, until they're observed or interact with their environment. Under normal conditions, these quantum effects don't appear at the macroscopic scale because of a process called decoherence. But in a white hole, with physics pushed to extremes, quantum effects might briefly become relevant at larger scales. Your body's matter could theoretically occupy multiple configurations or locations at once, creating a state where you wouldn't have a single definite physical form, but rather a probability distribution of possible forms. This wouldn't mean multiple copies of you existing simultaneously. It would be more like your matter becoming smeared across possibilities in a way that has no counterpart in our everyday experience. The transition from ordinary matter to these exotic states wouldn't be gradual. The extreme conditions of a white hole would trigger these transformations almost instantaneously. Your body wouldn't slowly melt or dissolve. It would undergo fundamental transformation at the subatomic level faster than any biological process could respond. The experience wouldn't be like burning or freezing or any other form of destruction we're familiar with. It would be a complete conversion of your matter into forms that have no analog in our everyday experience. Another fascinating aspect of matter transformation in white holes involves phase transitions. In everyday life, we're familiar with matter transitioning between solid, liquid, and gas phases. In extreme astrophysical environments, matter can undergo more exotic phase transitions to states like plasma or degenerate matter. A white hole would likely push matter through multiple phase transitions almost simultaneously, potentially revealing phases of matter that have never been observed even in our most extreme laboratory experiments. The nature of these transitions might reveal fundamental aspects of matter that remain hidden under normal conditions. For instance, physicists speculate about phase transitions that might have occurred in the early universe as it cooled from the Big Bang. These transitions can leave topological defects, irregularities in the structure of space that might manifest as cosmic strings or domain walls. Similar defects might briefly form within the matter of your body as it undergoes these extreme transitions. Some theoretical physicists have also considered how matter might behave in the presence of naked singularities, points of infinite density without an event horizon to hide them, which some models suggest might exist in white holes. Near such a singularity, matter might experience what's called spaghettification, but in reverse. Instead of being stretched into thin strands as with a black hole, matter might be compressed in some directions while being expanded in others, creating geometries that ordinary matter could never form under normal conditions. Certain theories in particle physics suggest that at sufficiently high energies, the fundamental forces of nature unify into a single force. This unification might briefly occur in the matter of your body inside a white hole. During this unification, the behavior of particles would be governed by more fundamental symmetries than those we observe in normal physics. These symmetries might allow for particle interactions that are impossible under standard conditions, potentially transforming the very identity of the particles that make up your atoms. Some speculative models even suggest that in extreme conditions like those in a white hole, the Higgs field, which gives particles their mass, might undergo a phase transition to a different value. This would change the mass of elementary particles throughout your body, fundamentally altering how matter behaves. Particles that are normally stable might become unstable, while others might change their properties entirely. The connection between matter and information would also become apparent in these transformations. According to some interpretations of quantum mechanics, the physical state of a system is ultimately a manifestation of information. In a white hole, as your body's matter transforms, the information describing its configuration would be processed in ways that have no counterpart in normal physics. This processing wouldn't just change what your matter is, but potentially what it could be, expanding the range of possible states your physical form could occupy. All of these transformations would occur so rapidly and completely that they would precede any possible conscious awareness of the changes. Your body wouldn't just be destroyed, it would be converted into forms of energy and exotic matter that bear no resemblance to the biological structures from which they originated. In this sense, the matter-energy conversion represents perhaps the most complete form of physical transformation conceivable in physics. These transformations remind us that matter as we experience it in everyday life is just one possible configuration of more fundamental components, a particular arrangement of particles and forces that happens to be stable under the conditions that prevail in our corner of the universe. In the extreme environment of a white hole, those components would rearrange into configurations so different from ordinary matter that they challenge our very concept of what physical existence means. While the transformations of matter inside a white hole reveal how different physical existence can be under extreme conditions, these extraordinary objects may serve an even more remarkable cosmic function. The radical reconfiguration of matter points to a deeper possibility, that white holes might not just be isolated cosmic oddities, but actual connections between different regions of our universe, or even bridges to entirely separate universes. This potential role as cosmic gateways represents one of the most fascinating aspects of white hole physics. Some theoretical models propose that white holes might function as endpoints of wormholes or Einstein-Rosen bridges. A wormhole, first mathematically described by Einstein and physicist Nathan Rosen in 1935, is a theoretical passage through spacetime that could create shortcuts between distant regions of space. In these models, matter that falls into a black hole in one region of space might, instead of being crushed into a singularity, pass through a wormhole and emerge from a white hole somewhere else. The mathematics supporting this possibility emerges from certain solutions to Einstein's field equations. The same equations that predict black holes also allow for these theoretical tunnels through space-time. The most famous solution, called the maximally extended Schwarzschild solution, describes a geometry where a black hole connects to a white hole through a bridge between them. This mathematical model presents a compelling picture, though most physicists believe such connections would collapse almost instantly due to instabilities, preventing actual travel through them. If you could somehow survive 5 seconds inside a white hole, which we've established is physically impossible due to the extreme conditions, you might be exposed to physics and conditions from entirely different cosmic regions, or even different physical realities. This is because the matter and energy a white hole expels must come from somewhere, and that somewhere might be a region with very different physical properties from our own. This connection to other regions raises fascinating possibilities about the nature of white holes themselves. Rather than being objects that exist within our universe, they might better be understood as junctions between universes, cosmic transfer points where matter and energy from one reality enters another. In this view, a white hole would represent the exit door from another universe into our own. Certain multiverse theories expand on this concept even further. Various approaches to theoretical physics, from string theory to inflation theory, suggest that our universe might be one of many in a vast multiverse. In some of these models, white holes could represent exit points from our universe into parallel realities where fundamental constants or physical laws differ from our own. The implications of such connections would be profound. Different universes might have different values for constants like the speed of light, the strength of gravity, or the behavior of quantum fields. They might even operate according to entirely different physical laws. If white holes do connect different universes, the matter and energy they expel would carry signatures of these different physics regimes. This might explain why white holes, if they exist, would be unstable in our universe. They would be importing physics incompatible with our own. The mathematics of certain white hole models suggests they might connect not just to different spatial locations but to different time frames as well. This temporal connection could work in various ways. For instance, a white hole in our universe might connect to a distant past or future state of our own universe. Alternatively, it might connect to a different universe with its own separate timeline running at a different rate or even in a different direction. If such temporal connections are possible, a theoretical survivor emerging from a white hole might find themselves in a completely different era. The 5 seconds spent inside could correspond to any duration in the external time frame, from microseconds to billions of years. This disconnection between internal and external time creates a situation where white holes could potentially function as one-way time machines, though not in a controllable or survivable manner. Some exotic cosmological models take the white hole concept even further, proposing that our universe itself might have begun as a white hole. According to these speculative theories, what we call the Big Bang might actually have been a white hole-like eruption of matter and energy from another reality or pre-existing state. The initial singularity from which our universe expanded shares certain mathematical similarities with how we model white holes. Both involve the explosive outward flow of matter and energy from an extremely dense state. If this white hole cosmology is correct, then studying white holes might provide insights into the earliest moments of our universe's existence. The physics that would govern a white hole might be similar to the physics that governed the first instance after the Big Bang, before conventional physical laws as we understand them had fully emerged. This connection suggests that white holes, while extraordinary, might not be entirely alien to the physics of our universe. They might represent conditions that once prevailed everywhere. What would this mean for a theoretical observer inside a white hole? If white holes do connect to other universes or timeframes, such an observer might briefly glimpse conditions from entirely different cosmic realities. They might witness physics from before the Big Bang or from parallel universes with different fundamental constants. This exposure wouldn't just be academically interesting, it would represent the first direct evidence of physics beyond our observable universe. Of course, as we've established, no observer could actually survive to report such observations. But the theoretical possibility remains fascinating. It suggests that white holes, if they exist, might serve as windows into otherwise inaccessible realms of reality. The matter and energy they expel would carry information about these other realms, potentially allowing indirect observation of their properties. The bridge-like nature of white holes connects to broader questions about the topology of space-time itself. In conventional cosmology, we typically model the universe as having a relatively simple, large-scale structure. But some theoretical approaches, particularly in quantum gravity, suggest that space-time might have a much more complex topology, with multiple connections between different regions. White holes might represent visible manifestations of these connections, places where the hidden complexity of space-time becomes directly observable. This perspective also relates to questions about the conservation of information in physics. One of the most important principles in quantum mechanics is that information cannot be created or destroyed, only transformed. Black holes create apparent problems for this principle because information seems to disappear behind their event horizons. If black holes connect to white holes in other regions of space-time, this could potentially resolve the information paradox. The information isn't lost, but is transferred elsewhere through the black hole-white hole connection. The potential for white holes to connect different universes also relates to questions about initial conditions and the apparent fine-tuning of our universe for complex structures like galaxies, stars, and ultimately life. Some theories suggest that if multiple universes exist with different physical constants, only those with the right combination of constants would develop observers capable of studying them. If white holes connect different universes, they might provide a mechanism for understanding how different combinations of physical constants play out across the multiverse. While all of these ideas remain firmly in the realm of theoretical physics rather than established science, they highlight the extraordinary possibilities that white holes represent. Even if we can never directly experience them due to their extreme conditions, their study pushes our understanding of physics to its limits and forces us to confront questions about the larger structure of reality. Some cutting-edge theories even suggest that white holes might play a role in resolving the ultimate fate of our universe. If our universe continues expanding forever, eventually reaching a state of heat death, where all useful energy is exhausted, white holes connecting to other universes might provide a theoretical path for cosmic renewal. Matter and energy from other universes could enter ours through white holes, potentially introducing new organized energy into an otherwise maximally disordered system. Regardless of whether white holes actually exist in our universe, thinking about them helps physicists explore the boundaries of our current theories. The study of these theoretical objects has contributed to developments in our understanding of general relativity, quantum gravity, and cosmology. White holes remind us that the universe may be stranger and more interconnected than our everyday experience suggests, with phenomena that challenge our most fundamental assumptions about the nature of reality. The possibility that white holes might bridge different universes or timeframes represents one of the most fascinating aspects of these theoretical objects. While we've established that human survival inside a white hole would be impossible, the theoretical implications of their existence continue to inspire some of the most ambitious and creative thinking in modern physics. The theoretical implications of white holes as bridges between universes lead us into even deeper physical territory. Beyond just connecting different regions of space-time, white holes would create environments where the very rules of physics as we know them would undergo radical changes. Inside such an environment, the fundamental physical constants and laws that govern our universe, the basic parameters that we take for granted in all our scientific work, would likely fluctuate or take on entirely different values. This breakdown of physical law represents perhaps the most profound aspect of white hole physics. In our everyday world, we rely on certain physical constants remaining, well, constant. The speed of light in vacuum, approximately 300 million meters per second, is perhaps the most famous example. This value doesn't change regardless of where or when you measure it in our universe. Other constants include the gravitational constant that determines the strength of gravity, Planck's constant that governs quantum behavior, and the fine structure constant that determines the strength of electromagnetic interactions. These constants form the bedrock of our physical theories. They appear in our equations as fixed values that don't change under normal circumstances. But inside a white hole, these supposedly immutable values might fluctuate or take on entirely different values. Spending 5 seconds in such an environment would mean experiencing physics where the rules, as we understand them, no longer consistently apply. The speed of light, for instance, might not remain constant in the extreme curvature of a white hole. While special relativity tells us that nothing can travel faster than light in vacuum, this principle assumes a flat or mildly curved spacetime. In the severely warped spacetime of a white hole, the local speed of light might vary from point to point, creating regions where causality as we understand it breaks down completely. Similarly, the gravitational constant, which determines how strongly masses attract each other, might take on different values in different regions of a white hole. This would create a situation where the strength of gravity itself becomes unpredictable, varying from one location to another. Objects with identical mass might exert completely different gravitational pulls depending on their precise location within the white hole's structure. These variations wouldn't be random, but would follow patterns determined by the extreme physics of the white hole. The tremendous gravitational gradients would create conditions where quantum gravity effects dominate. Quantum gravity represents the frontier of modern physics, the attempt to reconcile Einstein's general relativity, which describes gravity, with quantum mechanics, which describes the other 3 fundamental forces and the behavior of matter at small scales. In normal conditions, quantum gravity effects are only relevant at extraordinarily small scales, specifically at the Planck length, which is approximately 10 to the negative 35th meters. That's so tiny that we have no technology capable of directly probing physics at this scale. But in a white hole, the extreme conditions would amplify quantum gravity effects to macroscopic scales, making them directly relevant to the physics an observer would experience. Some theoretical physicists suggest that inside such extreme environments, symmetries that are broken in our observable universe might be restored. Symmetry in physics refers to situations where certain changes don't affect the outcome of an experiment. For example, the laws of physics work the same way regardless of which direction you're facing. That's a rotational symmetry. But some symmetries that we believe existed in the early universe have been broken as the universe cooled. In the extreme energy environment of a white hole, these broken symmetries might be temporarily restored, potentially exposing an observer to more unified forces and more fundamental physical laws than we can access in our current universe. For instance, the electromagnetic force and the weak nuclear force, which appear as distinct forces in our everyday world, merge into a single electro-weak force at high energies. In a white hole, even higher energy unifications might become apparent. The energy densities inside a white hole would likely exceed the Planck energy, the energy scale at which our current physical theories are expected to break down completely. At this scale, space-time itself is predicted to become quantized or granular rather than continuous. Instead of being an infinitely smooth fabric as described by general relativity, space-time would reveal its fundamental building blocks, tiny units of space and time that cannot be further subdivided. This quantization would create a situation where space and time themselves become quantum mechanical rather than continuous entities. Movement through space wouldn't be smooth, but would occur in tiny, discrete jumps. Similarly, time would progress in minimal ticks rather than flowing continuously. These discrete units would be extraordinarily small. The Planck time is approximately 10 to the negative 44 seconds, but the principle represents a fundamental revision to how we understand reality. In some speculative models, the laws of thermodynamics might temporarily reverse inside a white hole. The second law of thermodynamics, which states that entropy or disorder in an isolated system always increases over time, gives us the arrow of time that distinguishes past from future. But in a white hole, with time and causality already behaving strangely, entropy might locally decrease rather than increase. This entropy reversal would create bizarre situations where disordered systems spontaneously become more ordered. Scattered particles might spontaneously gather together. Complex structures might form from simpler components, and heat might flow from colder regions to hotter ones. These phenomena would appear to violate causality from our perspective, creating effects that precede their causes. The breaking of conventional physics would also affect the behavior of virtual particles and quantum fields. In quantum field theory, the vacuum isn't truly empty, but is seething with virtual particles that pop into and out of existence too quickly to be directly observed under normal conditions. These particles represent quantum fluctuations in the underlying fields that permeate all of space. In a white hole, these quantum vacuum fluctuations would be amplified to extraordinary levels. Virtual particles would become real particles with much longer lifetimes and higher energies than normally possible. The quantum foam, the theoretical structure of space-time at the smallest scales, might become directly observable rather than remaining hidden behind the limitations of quantum uncertainty. This exposure to the quantum foam might provide a glimpse into the underlying structure of reality that remains hidden under normal conditions. Some theories suggest that space-time itself emerges from more fundamental quantum entanglement relationships between basic entities. In a white hole, these fundamental relationships might become temporarily visible, revealing how space and time themselves are constructed from more basic components. Another fascinating aspect of physics breakdown in white holes involves what physicists call effective field theories. In our normal understanding of physics, we use different theories for different scales. Quantum mechanics for the very small, classical mechanics for everyday objects, and general relativity for the very large. These theories work within their domains because certain effects from other scales become negligible. In a white hole, this neat separation of scales would collapse. Quantum effects, relativistic effects, and classical effects would all become simultaneously important, creating a situation where no single existing theory could adequately describe what's happening. This represents not just a practical problem for calculation, but a fundamental limitation of our current understanding of physics. Some theoretical work suggests that in such extreme conditions, even the dimensionality of space might change. String theory, for instance, proposes that our universe actually has more than three spatial dimensions, with the extra dimensions normally compactified or curled up too tightly to notice. In a white hole, these extra dimensions might temporarily unfurl and become relevant to physics at observable scales. If this were to happen, the laws of physics would change in profound ways. Forces might decrease with distance according to different mathematical relationships. Conservation laws might work differently, and new types of particle interactions might become possible. An observer inside a white hole would essentially be experiencing physics from a higher dimensional reality that bears little resemblance to our familiar three-dimensional world. The constants of nature might also reveal themselves to be not truly constant, but rather emergent properties that arise from more fundamental processes. For instance, the value of the cosmological constant, which determines the expansion rate of the universe, might be seen to vary based on underlying quantum fluctuations that are normally averaged out over large scales. Some physicists have proposed that what we perceive as immutable physical laws might actually be more like local bylaws, specific to our region of the multiverse, rather than universal truths. If this perspective is correct, then inside a white hole, an observer might glimpse how these laws emerge from more fundamental principles, or even experience regions where different local laws apply. This breaking down of conventional physics creates a profound challenge for our understanding of reality. It suggests that the neat, orderly universe described by our current theories may be just a special case, a particularly stable configuration among many possible ways that reality could be organized. White holes would represent regions where this stability breaks down, revealing the more chaotic and dynamic reality beneath. For theoretical physicists, these breakdowns aren't just problems, they're opportunities. Places where our current theories fail point to new physics waiting to be discovered. The study of white holes, even if purely theoretical, helps physicists identify the boundaries of our understanding and develop new approaches that might eventually lead to a more complete theory of reality. The extreme physics of white holes reminds us that our current understanding of the universe is almost certainly incomplete. Just as Newtonian physics gave way to relativistic physics in extreme conditions, our current theories likely represent approximations that break down in the most extreme cosmic environments. White holes would be laboratories for testing the limits of physical law, if only we could survive to conduct the experiments. The incomplete state of our physical theories points to perhaps the most tantalizing aspect of white holes, their potential as sources of unprecedented scientific knowledge. While we've established that human survival inside a white hole would be physically impossible, this doesn't eliminate the theoretical value they might hold. If we could somehow gather and interpret information from these extreme cosmic objects, they might provide insights into fundamental physics that remain beyond our current experimental and observational capabilities. If an intelligence or instrument could somehow record and transmit data from inside a white hole, it might provide revolutionary insights into quantum gravity, that elusive unified theory physicists have been seeking for decades. Quantum gravity represents the holy grail of theoretical physics, a single coherent framework that would reconcile general relativity with quantum mechanics, explaining how gravity works at the quantum level. Currently, physicists have several candidate approaches to quantum gravity, including string theory, loop quantum gravity, causal set theory, and asymptotic safety. These different frameworks make distinct predictions about how physics behaves in extreme gravitational environments. The interior of a white hole would be precisely the kind of environment where these different theories would make noticeably different predictions. Data from inside a white hole could potentially tell us which, if any, of these approaches is on the right track. For instance, string theory predicts that at very small scales, particles aren't point-like, but are actually tiny, vibrating strings. Different vibration patterns produce different particles. In the extreme conditions of a white hole, these strings might behave in ways that would be directly observable, confirming or refuting key aspects of string theory. Similarly, loop quantum gravity, another leading candidate, suggests that space itself has a discrete, granular structure at the smallest scales. Inside a white hole, where space-time curvature reaches extraordinary levels, this granular structure might become apparent in ways that could be measured. The precise pattern of this granularity would provide strong evidence either supporting or contradicting the loop quantum gravity approach. Beyond just distinguishing between existing theories, white hole data might reveal entirely new physics that nobody has yet imagined. The history of science shows that when we push into extreme new regimes, whether extremely small, large, hot, cold, or dense, we often discover phenomena that force us to revise our fundamental theories. White holes represent perhaps the most extreme environment conceivable in physics, making them potential sources of truly revolutionary discoveries. The extreme conditions might reveal whether string theory, loop quantum gravity, or other candidate theories of everything correctly describe physics at the most fundamental level. They might also help resolve major outstanding questions in theoretical physics, such as the information paradox associated with black holes. The black hole information paradox hinges on the apparent conflict between quantum mechanics, which says information cannot be destroyed, and general relativity, which suggests information falling into a black hole is lost forever. Physicists like Stephen Hawking spent decades wrestling with this problem. If white holes are somehow connected to black holes, as some theories suggest, they might provide the missing piece of this puzzle by showing how information that falls into a black hole might eventually emerge from a white hole. Another fundamental question that white hole data might help resolve is the measurement problem in quantum mechanics. This problem concerns how quantum systems, which exist in superpositions of multiple states simultaneously, appear to collapse into a single definite state when measured. Various interpretations of quantum mechanics, from the Copenhagen interpretation to the many worlds interpretation to quantum decoherence, offer different explanations for this phenomenon. The extreme conditions inside a white hole might create situations where these different interpretations make distinct, testable predictions. Data from such environments could potentially help physicists determine which interpretation best describes quantum reality. This would represent a major breakthrough in our understanding of quantum mechanics, which, despite its extraordinary success as a predictive theory, remains mysterious in its foundations. White hole data might also provide insights into the fundamental nature of spacetime itself. Is spacetime fundamentally continuous, as general relativity suggests, or quantized, as many approaches to quantum gravity propose? Does it emerge from more basic quantum entanglement relationships, as suggested by certain theoretical frameworks? The extreme curvature inside a white hole would create conditions where these different models make distinct predictions that could be tested with the right data. Some physicists speculate that white holes, if they exist, might preserve information about previous cosmic cycles or universes. According to certain cosmological models, our universe might be just one in a series of universes that expand, contract, and are reborn in cyclic patterns. If white holes connect different cosmic cycles, they might contain information about previous cycles that would otherwise be completely inaccessible to us. This possibility relates to questions about what happened before the Big Bang, a question that conventional physics struggles to address since time itself may have begun with the Big Bang. If white holes preserve information from before our universe's beginning, they could provide a window into this otherwise inaccessible domain, potentially revolutionizing cosmology and our understanding of cosmic origins. The unique temporal properties of white holes might theoretically allow observation of both the extreme past and future simultaneously. If white holes do involve some kind of time reversal or connection between different time frames, data from their interiors might reveal information about the ultimate fate of our universe. This could help resolve questions about whether the universe will expand forever, collapse back into a big crunch, or undergo some other transformation in the distant future. While human survival inside a white hole would be impossible, advanced hypothetical technologies might someday allow for shielded probes that could gather even a fraction of a second's worth of data from near a white hole's event horizon. Even this limited data could potentially revolutionize our understanding of fundamental reality. What might such technologies look like? They would need to be fundamentally different from anything we can currently build. Conventional materials and electronics would be instantly destroyed by the extreme conditions. However, theoretical physicists have speculated about exotic materials and information processing systems that might be more resilient. For instance, some have proposed the theoretical possibility of computing systems based on topological quantum states. These states derive their properties from global features that remain stable even under significant local disturbances. While current topological quantum computers are extremely primitive and require temperatures near absolute zero, more advanced versions might potentially withstand more extreme conditions. Other speculative approaches involve what physicists call quantum error correction, techniques that protect quantum information against environmental disturbances. Nature itself appears to use some form of quantum error correction in certain biological processes. Advanced versions of these techniques might eventually allow for the creation of measurement devices that could maintain their integrity long enough to record meaningful data even in extremely hostile environments. Even more speculative are proposals for probes made of exotic states of matter that don't currently exist in our laboratories but might theoretically be created in the future. These might include various forms of quantum matter with properties specifically designed to remain stable under extreme gravitational and radiation conditions. Regardless of the specific technology, any device capable of gathering data from a white hole would represent an engineering achievement far beyond our current capabilities. The development of such technology would likely require breakthroughs in materials science, quantum information processing, and fundamental physics that might take centuries or even millennia to achieve. Despite these enormous challenges, the theoretical value of such data makes the concept worth considering. Throughout the history of science, seemingly impossible measurements have eventually become possible through technological innovation. While white hole interiors represent an extreme case, the pattern of scientific progress suggests we should never say never when it comes to future measurement capabilities. Even if we never manage to directly probe white hole interiors, their theoretical study remains valuable. The attempt to understand these extreme objects pushes our theories to their limits, forcing physicists to confront the boundaries of our current understanding. This theoretical work has already contributed to developments in our understanding of quantum gravity, cosmology, and the foundations of physics. Moreover, if white holes do exist somewhere in our universe, they might indirectly reveal themselves through their effects on surrounding space. The matter and energy expelled from a white hole would have distinctive signatures that might be detectable with sufficiently advanced astronomical instruments. While we haven't observed anything that definitively looks like a white hole so far, future observational technologies might change that. The James Webb Space Telescope, launched in 2021, represents a major advance in our ability to observe distant cosmic phenomena. Future instruments will be even more powerful, potentially allowing us to detect phenomena that currently remain hidden. If white holes do exist, these advanced instruments might eventually detect their signatures, providing indirect access to some of the physics they contain. White holes remind us that the universe likely contains phenomena far more extreme and exotic than what we've directly observed so far. The fact that they emerge mathematically from our best current theories suggests that even if they don't exist in exactly the form we currently imagine, something with similar properties might be out there waiting to be discovered. The study of these theoretical objects connects to the broader human impulse to push boundaries and explore the unknown. Even if we can never directly experience a white hole, the attempt to understand them stretches our minds and extends our theoretical grasp. Each step toward comprehending these extreme objects represents a small advance in our overall understanding of the cosmos and our place within it.